All right, so let's start this one. This one off the top of my head, I can't give you the reactions. And that's going to be generally the case for most of these problems. So you're going to have to do that work you did at the beginning of the course in stats. We're going to have to find the reactions just to get started. Okay? So I'm going to try to do this off to the side here and start with just drawing a free body diagram of the original. There is a load of 600 pounds right in the middle. And about halfway over, there's this applied moment that's 4 kip feet. Oh, I'll put the dimensions in too. So this is 10 feet, and then this is 5 and 5. And then I'm going to assume reactions.
Are you changing all of the kips?
No, I just didn't want to write 4,000. I'm sorry, I was lazy. I may change it to kips when I do all my equations, though.
Yes, sir.
So I'm going to assume some forces here. And I'm going to do something a little different. Just because I know I'm going to draw a shear diagram, I'm going to apply a positive shear force at A, and I'm going to apply a positive shear force at B. Those are my sign conventions, right? That's positive for shear. Okay? Not just reactions. I'm solving for shear forces now. I can do that. So I'm going to do that. I'm going to, I think I'll sum moments about A to get started. So I'm going to use right-hand rule for my sign convention. And we'll sum moments at A. Make sure the beam is in equilibrium. So this 600-pound force, which I'll now call 0.6 kips, creates what kind of moment about A? Positive or negative? Negative. So that'd be negative 0.6 kips. And what's the moment arm? Distance from A to there? 10 feet. I'm summing moments, so here comes a moment of 4 kip feet. Is that positive or negative with my sign convention? Negative. So that'd be minus 4 kip feet. And then I have the shear at B. What kind of moment does that create? Negative. And what's the distance from A to B? 20. So now I will solve for the shear. I said A, I meant B, sorry. What is the shear at B? You guys have to help me with that. 4.6 divided by 2 is 2.3?
2.5.
Oh, I did that wrong, yeah. What is it? Negative 0.5? Really? The negative I like, but is it you sure it's 0.5? Okay. So since I'm solving for shear and I always assume positive, what does that mean? The shear at B is negative. So when I draw my shear diagram, what should the shear at B be? BB. What should the shear at B?
Positive 0.5.
How would you follow it? It's got to be 2 B's, right? What would the shear at B be?
0.5 kips up.
What is the sign of the shear at B?
Negative.
Negative. Thank you. I knew I could think of it a different way. All right. So if we sum forces now in the y direction, what do we get? Well, we get the shear at A acting up. The shear at B is what when I sum forces? Positive or negative? Negative.
Negative.
And my 0.6 force is negative. So what is the shear at A? Well, I put my negative 0.5 in here. It becomes a positive. So the answer is 0.1. Does that sound good? Positive. Isn't it positive?
Yeah.
Yeah. So now I know I'm going to start at a positive value of shear and go to a negative value of shear. So now I'm going to come over here and I'm going to make a template so I can construct my diagram. I'll have my starting point and my end point. And now I probably want lines to indicate other important things. So you're probably going to have one at every applied load because we know things change from the left to the right. So I'll add that. That's the midpoint. And on my moment diagram, I'm going to have an applied couple here. So that's going to make a jump in my moment diagram. So I probably want to also include that. Then I'll make a axis for my positive x, my positive shear. You know, these numbers are coming out a little small for me. I think I'm going to go back to writing this as hundreds. I'm going to go back to pounds. Is that okay?
Yes.
So I'm going to come over here and say that this is in pounds. I think it'll be a little easier to do our calculations. So what will be the shear at A in pounds? Well, it's 100, and it's positive. Where else do I know the shear? At B. And it's what? Negative 500. Now I got to figure out what's happening in the middle. Now remember, we've got our handy friends. The change in shear is the area under the load curve. And then the slope of the shear diagram is given by the value of the load. So let's start with this first segment under 10 feet. What's the area under the load curve? 0. There is no load. So if I started at 100 pounds, I'm going to stay at 100 pounds. And the slope of that diagram is given by the load, and the load is 0. So that's a horizontal curve. So the shear is constant over the first 10 feet. Now, as I go from the left side to the right side, I know the change in shear is equal to this applied force. And that's what kind of value? Positive or negative?
Negative.
Negative. So I'm going to start at 100, and I'm going to subtract 600. I get to minus 500. The change in shear is area on the load curve. What is the area under the load curve for the forces? Everywhere here. 0. So there's no change. That's great. So there's no change. And then we know the slope is given by the load. And the load is 0. So my shear looks like that. So now that we've constructed the shear diagram, it seems to be reasonable. Let's use our relationships to construct the moment diagram. Give myself some room to draw this. So I'll put a positive axis for x on that. I'll indicate what positive moment is, and I'll say my units are in pound feet. All right, starting. Let's see what I know anything. What's the moment at A? Unless you have an applied couple there, the moment at external pins and rollers is going to be 0. Now, if I move this roller set up interior, the moment at that support is not 0 necessarily, because the cantilever end can bend and creates the moment over the support. But in this case, we're going to start at 0 and we're going to end at 0. So let's use our relationships. We know the change in moment is the area under the shear diagram. We also know that the slope of the moment diagram is equal to the shear. Now, one of the things that we've done a few times now is we've also added that we know that the change in shear is equal to an applied load, right? We're going to also know that the change in moment is going to be equal to an applied couple. And we got one of those. So keep that in mind as we approach. So starting with the first segment here, I'm looking at the first 10 feet. I got a constant shear, which is good. I've got no applied couples, so I'm good to go. And to calculate the change in moment is the area of the shear diagram. And that would be what?
1,000 pounds.
Right, 10 times 100 or 1,000 positive. That'll be pound feet. And the shape of the curve is given by the shear, and the shear is constant and positive. So I get a nice constant positive slope. So it's triangular. What's the change in moment? Can I do it over the next 10 feet? No, because I've got this guy. So I'll have to go just to the left of it. So I'll go just over this 5-foot interval. So what's the change in the moment just over this part of the shear diagram? It'd be negative 500 times 5. That's negative 2,500, right? What is 1,000 minus 2,500? Minus 1,500. What's the shape of the graph in between? Well, it's given by the shear, and the shear is constant and negative. Now, in our course, we're not really concerned with the moment diagram crossing the axis and identifying that point. So you don't have to worry about it. We only care when the shear diagram crosses the axis. Having the moment diagram crossing the axis indicates something else, but it's beyond the scope of this course. It's leaning towards the actual deflection of the shape. And we won't worry about that for a couple weeks or months. Month. A couple months will be in Christmas time. That you won't be concerned about this at all. Well, most of you won't. Now what happens? I go from this side to this side, and what happens?
Positive.
Yeah, that's a clockwise moment, so that causes a positive jump. So I'm going to have negative 1,500 plus 4,000 brings me to 2,500. I don't think I've got my graph just right, but you get the idea.
Wait, can you explain why that's a positive jump?
Clockwise is positive. It's just the rule.
But isn't that's a
It's not a bending moment. It's an applied moment. It's just like an applied force. What kind of shear is this? It's not. It's force.
right?
It creates a shear. So this applied moment creates a change in moment.
Okay.
So I just memorized it. Clockwise is positive.
Okay.
Just
oh,
like
yeah. I used to have a thing like if you're on the left side of the circle, it's up. So that's
there is no side of this.
Yeah.
You're actually looking at the moment right before it's applied and the moment right after it's applied.
Okay.
And that change in moment is equal to that value, and clockwise makes it go positive.
Yes.
I'll show you another way that, if you can't figure that out, I'll show you a way to figure it out in a second.
Okay.
So now what do? The change over this segment is given by the area of the shear diagram, and that area is minus 2,500. So we get to 0. And the slope is constant and negative, and it should be the same slope as this segment here. I may not get it perfectly right, but you get the idea. So that's our moment diagram. If you did this using the equation method, how many sets or how many moment equations would you have to write? 3. I think this is a lot easier than doing that. Because my question would then be to you, what's the maximum moment in the beam? Where does it occur? It's 2,500, and it occurs just to the right of the applied couple at 15 feet. If you had just a bunch of equations, you didn't have to figure out what's the max of this equation in this range, and what's the max of that equation in this range, and what's the max of this equation in its range, and which one is the maximum, and it's like, this is a lot easier. This graphical technique has some real power to it. Now, if you got to this point right here and you're trying to decide whether to go up or down, here's a little trick. The next segment over is going to go up or down. Down. So if you drop down and then went down some more, you're going to end up with a huge negative moment at a pin. That ain't happening. If you can't decide, just look ahead at what's coming. And you know where you've got to land. That's another way to do it, to make you feel better about it. I've just memorized clockwise is up. Okay. Any questions about this one? I think we should continue forward, don't you? Unless you guys want to do something else. I need to move all my monuments on my